Exercise. If the surface of a sphere of radius small a is kept at a fixed distribution of electric potential of the form U equal to capital F of theta. Then find the potential inside and outside the spherical surface, assuming the space inside and outside the sphere to be free of charges. So let me read out the problem once again. If the surface of a sphere of radius small a is kept at a fixed distribution of electric potential of the form U equal to F of theta, then find the potential inside and outside the spherical surface, assuming the space inside and outside the sphere to be free of charges. We can see from this particular given question that the charge, the distribution is independent of phi. Okay, so there is azimuthal symmetry. Okay, so solution. Here, the surface of the sphere of radius a is kept at a fixed distribution of electric potential of the form U equal to F of theta. Equation number 1. So this means that our given problem is independent of phi, so we need not worry about the phi part of the solution. The given boundary conditions are: number 1, U is equal to F of theta at R equal to A. This we call equation number 2A. And the second boundary condition is, we assume that the potential goes to 0 at infinity. That is, U becomes 0 at R equal to infinity. That is, potential at infinity is 0. This we call equation number 2B. Okay. This is 2A and this is 2B. That is, potential at infinity is 0. Okay. So we have to find the potential inside and outside the spherical surface by assuming that the space inside and outside the sphere is free of charges. So let us consider first the region outside the sphere. So case number one, outside the sphere. Outside the sphere. Okay. So here we are given that the space outside the sphere is free of charges. So let me write it here. Is the space outside the sphere is free of charges. Therefore, at each point, outside the sphere, Laplace equation must be satisfied. Laplace equation must be satisfied. That is Laplacian of the solution U should be equal to 0. Okay. And we already know, let me write it on a new sheet of paper. The Laplace equation must be satisfied, and we already know the solution. The general solution of this equation, the Laplace equation in spherical polar coordinates, is given by U equal to summation over n, an r to the power n plus bn r to the power minus n minus 1 and pn cos theta. And we do not consider the phi dependent part, because we can see from the given question that our problem is independent of the azimuthal angle phi. That is, there is azimuthal symmetry. Okay, so this we call equation number 3. The boundary condition, the boundary condition 2b requires that the solution be free of any positive power of R. Okay, let us see the boundary condition once again. So what is the boundary condition number 2? The boundary condition number 2 says that as R tends to infinity, the potential should tend to 0. That is, at R equal to infinity, the potential is 0. So here is the expression for the potential. When you put R equal to infinity, here, when you put R equal to infinity, this term, here n goes from 0 to, so when R goes to infinity, this term diverges, means this term goes to infinity. Okay, but we already know that when R goes to infinity, U should go to 0. That means this term should not be there, because this particular term, when R goes to infinity, this term goes to 0. So this is the term which satisfies the boundary condition 2b. So this term can be present, but this term should not be present. That means an should be 0. So this is what we mean when we say the boundary condition 2b requires that the solution be free of any positive power of R, thereby giving an equal to 0. Okay, this term should not be present because when R goes to infinity, U should go to 0. But when R goes to infinity, this term goes to infinity. So this term should be absent. And the only condition that this term can be absent is when an goes to 0. Okay. Hence, equation 3 reduces to U is equal to summation over n from 0 to infinity. This an is 0, so what remains is only this term. So Bn R to the power minus n minus 1 Bn cos theta. This R to the power minus n minus 1, we can bring it to the denominator. So this can also be written as summation n from 0 to infinity n by R to the power n plus 1. Minus n minus 1 means in the denominator it becomes R to the power n plus 1. And Pn cos theta. We call this equation number 4. Okay. Then how do we determine this unknown constant Bn? This unknown constant Bn is determined by using the first boundary condition. That is, U is equal to f of theta at R equal to A. This Bn we determine by using the first boundary condition. That is, U is equal to f of theta at R equal to A. So let us calculate B. Okay. So the unknown constant constants Bn are determined by using boundary condition 2a. So substituting R equal to A in equation 4, we get, substituting R equal to A in equation number 4, what do we get? We get f of theta. This is the value of U at R equal to A. We can call it some function of cos theta. Okay. This is equal to summation, we put R equal to A here. Summation Bn by e to the power n plus 1 Bn cos theta. This we call it equation number 5. Now, how do we solve for Bn from this? Very simple. We use the orthonormality property of Legendre polynomials. Okay. So how do we do that? We multiply both sides by, so multiply by Pm. So multiplying. Before that, we can do one more simplification. That is, we can replace cos theta by x. Okay, let us do that first. So if we replace cos theta by x in equation 5, we get f of x, this f of cos theta, f of x, this is equal to summation over n, this is summation over n, this is summation over n, Bn divided by e to the power n plus 1 Bn of x. We can call this equation number 6. Now we solve Bn by using the orthonormality property of Legendre polynomials. So multiplying both sides. Multiplying both sides by, we have Pnx here, so we multiply by Pmx, and integrating between the limits, -1 to +1, we get x is cos theta, and cos theta can take values from only -1 to +1. So we get, so on the left hand side, we multiply f of x by Pmx, then integrate with respect to x from -1 to +1. Okay. This is the left hand side. Then the right hand side, we can take the summation outside the integral sign. So summation over n. Then this bn and a, these are also constants. So we can also take it outside the integral sign. So a to the power n plus 1 integration bnx bmx from -1 to 1 with respect to x. Okay. And from the orthonormality property of Legendre polynomials, we know that this is nothing but 2 by 2n plus 1 delta mn. So let us use that property. Okay. So this is equal to over n. So this is equal to summation over n bn by a n plus 1, and this part from the orthonormality property of Legendre polynomials, we know that this is 2 divided by 2n plus 1 delta mn, where delta mn is the Kronecker delta, and this delta mn, this is equal to 1 when m is equal to n, and this is equal to 0 when m is not equal to n. So this is equal to bm plus 1, bm to the power n plus 1. I repeat, bm to the power n plus 1. Okay. 2 divided by 2 m plus 1. Okay, so delta mn means all the n's which are present here are replaced by m, and we remove the summation sign. Okay, this is fine. So we have obtained this is equal to this. Now to solve bm, we take the remaining terms towards the right. This implies bm is equal to we keep this integration, and then we take these two factors towards the left. Okay, bm is equal to a to the power m plus 1 divides m plus 1 divided by 2. Okay, then integration, this integration from -1 to +1 f of x mx dx. Okay, so bm, this constant is equal to am plus 1, a to the power m plus 1 to 2 twice m plus 1 by 2, this. And m stands for any index starting from 0 to infinity. So we can replace m by any other index, say n. So replacing m by n, we get bn is equal to e to the power n plus 1 twice n plus 1 by 2 integration -1 to 1 f of x pnx dx. Why do we want to change m to n? We want to change m to n because in equation number 4 we have bn here. Okay, so that is why we change from m to n, because we want to substitute that expression for bn in this particular expression. Now let us put back x equal to cos theta. So as x equal to cos theta dx equal to minus sin theta d theta, we have bn is equal to a to the power n plus 1 by twice n plus 1 by 2 integration x is cos theta. Okay, so this we can take it as from 0 to pi f of cos theta pn cos theta sin theta d theta. Okay, and this is equal to a to the power n plus 1 twice n plus 1 by 2 integration 0 to pi f of theta pn cos theta sin theta d theta.
Sir,
Yes. Let me post. So this is the expression for bn. So a to the power n plus 1 twice n plus 1 by 2 integration. So f cos theta is nothing but capital F theta pn cos theta sin theta d theta. This we call equation number 8, and this we call equation number 7. So substituting this value, substituting this value of bn in this expression of u, we get our final answer. So substituting the value of bn in equation 4, we get u is equal to, here, equation 4 is this. Equation 4 is this. U is equal to summation this. Okay. Summation, here we have twice n plus 1 by 2 a over r to the power n plus 1 pn cos theta, then this integral 0 to pi f theta pn cos theta sin theta d theta. This we can call equation number 9. Okay, this is the expression for a potential. This is the potential. This is the potential outside the sphere. Outside the sphere. This is the value of the potential outside the sphere. Okay, that is fine. Okay. Let me stop the recording here.